we are talking about one of the such device, absorption spectroscopy based device, which is very much used, is the pulse oximeter. And the technique involved is basically to capture the information related to hemoglobin and oxyhemoglobin. Okay, the hemoglobin itself is also less reduced hemoglobin. Okay, and oxyhemoglobin. What we found from their absorption characteristics of this, structures, molecular structures, we found that there is a significant difference at around 660 nanometer wavelength of light in terms of reduced oxyhemoglobin here, absorption coefficient or extinction coefficient, and reduced hemoglobin is over here, there is one isosybistic line around 800 nanometer. Both this oxyhemoglobin and reduced hemoglobin shows almost equal, extinction coefficient, and then around 940 nanometer oxyhemoglobin has more extinction, reduced hemoglobin has less extinction. So basically these wavelengths are used, 660 nanometer, sometimes even 805 nanometer, okay, and 940 nanometer. These wavelengths are used to determine concentration of oxyhemoglobin, reduced hemoglobin, and from there we can derive a saturation parameter. So basically that there are two wavelengths that what we use. Now let us say C is the total concentration of hemoglobin molecules. Let us say C is okay, total, okay, molecules, okay, and AS is oxygen saturation, let us say. Then we can say, based on this oxygen saturation and this C parameter, as we know, basically you see, if oxygen saturation is 100%, let us say 1. So what it means, oxyhemoglobin, so 1 minus S into C will be reduced hemoglobin concentration overall, total, and if S is 1, reduced hemoglobin will be 0, and the corresponding oxyhemoglobin will, it corresponds to this, this part, directly S, okay, S into C. So one, this thing. Secondly, the transmission characteristics, okay. We also know that we know I of transmitted at let us say lambda 1, okay, at lambda 1, which is equal to I 0 lambda 1, when through a gas through a let us say cuvette of length L, if light is length or this length D. So if this is a cuvette which blood is filled and light is transmitted 0 lambda 1, and it get transmitted lambda 1, okay, this is and this is, let us say, D, then we know that this will be equal to extinction, will come into picture. And there are two components. One is hemoglobin, it consists of hemoglobin plus oxyhemoglobin. Of course, there are other constituents. At present, we are not we are neglecting those aspects. We are just assuming that blood has hemoglobin and oxyhemoglobin, no other absorption or scattering medium is present, then we can represent this as per the Beer-Lambert's law. It is equal to alpha, basically absorption, right, overall total absorption will be equal to alpha into D, where this alpha value is due to oxyhemoglobin and hemoglobin coming into picture, isn't it? Alpha is nothing but absorption coefficient, and let us say for hemoglobin it will be 1 minus S into C and into sigma of hemoglobin, right, at lambda 1, okay, of hemoglobin, correct. So that will be alpha, isn't it? Constant, what is alpha? Sigma absorption cross section into concentration of molecules, right, sigma into n, where sigma is absorption cross section, right, and n is, this is what we in the previous class, right, numbers per molecules per centimeter cube, let us say, and absorption cross section is in centimeter square. So alpha for hemoglobin is this, and alpha plus oxyhemoglobin will be S into C into sigma oxyhemoglobin, correct, of at lambda 1, okay, right. So this is one aspect, and similarly for so this is one, the C is total concentration of hemoglobin, S is oxygen saturation, right, and similarly, so if I treat this, and secondly I take D, let us say optical density, okay, optical density as D lambda 1 is equal to natural log of I 0 lambda 1 corresponding to I t lambda 1, okay. If I take, what is this, D lambda 1 will be equal to alpha into D, correct, alpha into D, isn't it? Use this equation and define D lambda 1 optical density is natural log of I 0 lambda 1 by I t lambda 1, automatically it will become equal to alpha D, okay, right. Similarly for lambda 2 wavelength, D lambda 2 will be natural log of I 0 lambda 2 I t lambda 2, right, and that will be for alpha at lambda 2 into D, correct. Alpha at lambda 2 will be 1 minus S into C sigma of hemoglobin or at lambda 2, and S into C into sigma, right, at lambda 2, correct. Is it okay, these two equations, okay. So if okay, so of course from this value, so we have we know what is input intensity light, what is transmitted intensity we can measure, okay, using a power meter optical sensor. From there we can estimate what is D lambda 1 and D lambda 2, and D lambda 1 and D lambda 2 contains these two parameters, okay. So D lambda 1 as already I have described above, okay, which is 1 minus S C sigma of hemoglobin at lambda 1 plus S C sigma of hemoglobin oxyhemoglobin at lambda 1. Similarly, d lambda 2 is 1 minus S into C sigma of hemoglobin at lambda 2 plus S C sigma of oxyhemoglobin at lambda 2. Okay. So, this is the we can estimate. Okay. Sorry, into D will come, no, overall into okay, into D density, sorry, of path length, correct, into path length, okay, will come. So, from this, okay, we can simplify this mathematical equation. We can derive as right, sigma hemoglobin at lambda 1 minus sigma hemoglobin at lambda 2, okay, D12. Okay. What is D12? D12 is D1 lambda 1 divided by D2 lambda 2. Okay, D12. Okay. So, so this is sigma divided by sigma of oxyhemoglobin at lambda 2 minus sigma of hemoglobin at lambda 2 right, D1 into D12 minus sigma of oxyhemoglobin at lambda 1 minus sigma of hemoglobin at lambda 1. Okay. This is, of course, just it's a mathematical, right, and just rearrangements of this, right, terms will end up. So, we know sigma of hemoglobin, okay, based on the database. We know sigma of oxyhemoglobin at lambda 1, lambda 2 respectively, as well as we know D12 based on our measurements, correct. Based on the measurements, we know input intensity, output intensity at lambda 1 through this cuvette as well as for at lambda 2. So, you can estimate D1 lambda 1, D2 lambda 2, and from the D12 substitute all these values, we will be able to, right, estimate the saturation value. Okay. So, that is the idea, and this technique is used in order to derive right, the parameters related to saturation. So, now when we are capturing this information using pulse oximetry, basically it consists of two light sources. So, in a pulse oximeter, okay, so right, so the light source will transmit through the finger, and the photodiode on the other hand detector will detect, and if the photodiode has sensitivity for both the wavelengths 660 nanometer as well as 940 nanometer, hence it will be able to capture the information using right, transmission characteristics. Now, when the light is transmitted through this skin, tissues, other things, and venous blood, arterial blood, everything to the right transmitted, it has some fixed component of skin tissue scattering, venous blood scattering, arterial blood scattering. Okay, and in order to right, capture the information of the blood which is getting supplied afresh, what is the amount of oxygen it is carrying or oxygen saturation, what is done, both this light sources rad as well as IR sources will be modulated. Okay. So, let us say this is rad means 660 nanometer light source is modulated with frequency of right 1 kilohertz, let us say. Okay. So, basically every 1 millisecond one pulse is there, and with right with 50 microsecond as the pulse width. Okay. So, every right 1 millisecond 50 microsecond, this should not be here, I think this should be here. Okay. Correct. So, every 1 millisecond we will see 50 microsecond pulse width, okay, of this red color light, and similarly infrared light has slightly right shifted, phase shifted such a way that right every 1 millisecond. However, from this red color pulse every 500 microsecond there is an infrared pulse. Okay. So, what we are measuring right within 1 millisecond, right at a repetition rate of 1 kilohertz, we are capturing every 1 millisecond one signal, right, both these two signals which we are capturing. Now, the oxygen right the heart pumping rate is at approximately it will be right 60 to 70 right frequency with a 60 to 70 sorry, not 60, but every 800 to 900 millisecond. Okay, that is one right pump right input pumping. So, that means within that 800 millisecond of this pump pulse right of blood being supplied, so many times we are measuring how the oxygen variation comes into picture, right. The blood is being pumped and heart is pumping is rate is such that it is approximately right 800 right if you see the pump heart ECG waveform, it is around 800 right millisecond it will take, okay, to complete one waveform. That means one pump cycle is of the order of 800 right 700 800 millisecond cycle. So, every time one so accordingly the blood supply right the phrase blood supply is working with that pulsating rate, and within that phrase blood supply the measurements are captured. Of course, this blood supply which is right getting pulsating blood supply is trying to capture basically the signal variation in oxyhemoglobin blood with respect to right this measurements. So, we will see corresponding to the pulse volume right which is being supplied by the heart in terms of blood right corresponding to that variation in the blood volume, we will see the corresponding signal right of each point within this pulse. Many number of times we will see the signal being captured by the photo detector corresponding to red and infrared pulsating, right. So, accordingly we will see as right DC component will always be there corresponding to the scattering losses, some constant absorption and scattering losses through this finger, plus and over and above due to the absorption of the oxyhemoglobin and hemoglobin, the pulsating nature from the output of this photodiode will also be captured, and this signal right which is pulsating right is DC it consists of two things, 660 let us say light at 660 nanometer DC component and a corresponding AC component which is nothing but a small variation over the fixed intensity, okay, AC component of at 660 nanometer. Similarly, for 940 nanometer also we will capture the AC as well as DC component from this right measurements, and the R value is derived, okay. And empirically this R value which is derived is given by empirically, it is correlated with oxygen saturation. Of course, from absorption measurement also what I derived in the previous equation we can derive this, but in right pulse oximeter the same aspect, okay, saturation can also be derived by fitting an equation, empirical relationship between between the parameter R which is captured here by based on our right measurements at 660 and 940 nanometer, and oxygen saturation is captured over here. So, this is the approach which is used in pulse oximetry. Now, due to the presence of carboxyhemoglobin also, it also plays some role in terms of the saturation measurements, etc. We generally neglect this, we only capture the information for oxyhemoglobin and reduced hemoglobin, we neglect methemoglobin as well as carboxy hemoglobin parameters, okay, from our measurements. We assume that those two parameters, the presence of carboxyhemoglobin and methemoglobin is very small. So, it is quite negligible, it will not affect our measurement is our right, it is our assumption. In fact, at this wavelength 660 nanometer as well as 940 there is some absorption by these molecules, but since the concentration is too small we neglect those parameters. But if sometimes if the carboxyhemoglobin starts increasing due to the absence of let us say due to maybe the presence of carbon monoxide, etc., okay, gases. So, in a suffocating environment where the oxygen starts the supply is starts decreasing. However, because of the human right breathing or within an closed environment where carbon monoxide or carbon dioxide gases starts increasing in terms of concentration, then carboxyhemoglobin starts increasing, and when carboxyhemoglobin starts increasing the saturation curve, okay, if we measure means partial pressure of oxygen and this is saturation of oxygen sorry. So, generally when in a when the carboxyhemoglobin is not playing any role, it is like this and we know that this value is around 13 kilopascal, this value is around let us say 10 kilopascal or so, okay, and it starts decreasing exponentially with the decrease in oxygen concentration in terms of partial pressure below 10 kilopascal, the saturation parameter decreases very fast, okay. In the presence of carboxyhemoglobin, what happens, this curve it shifts towards left, it shifts. That means, the similar curve will in the presence of large amount of carboxyhemoglobin, the similar curve, right, will be there, but now it is shifted, okay, shifted like this, okay. So, so what will happen when it shifts? You can imagine that the actual amount of oxygen associated with hemoglobin, okay, decreases, okay. It will use, right, it shifted, the curve has shifted left side. So, actual amount of partial pressure of oxygen in hemoglobin decreases, okay, it gets coupled with carboxy, right, those molecules. So, carboxyhemoglobin starts increasing, but the saturation parameter which is captured will not be able to see this information, right. It will still measure let us say even with a low oxygen with hemoglobin, it will still measure higher saturation parameter, okay, correct. See, the oxygen level has decreased, but the saturation parameter is large, right. What it means, that the oxygen which is really required, oxyhemoglobin which is required for the tissue to carry on its metabolic activities decreases, okay. So, there is a oxygen deficiency. However, saturation does not measure this, capture information, is not it, because it will always give you oxygen saturation is around 90%, 95, but actually it has decreased by amount, right, because although oxygen saturation is not shown, it is not decreasing, but the partial pressure of oxygen associated with oxyhemoglobin has decreased, is not it. So, how will we capture such information, right. Right. So, in conventional pulse oximetry we cannot capture this information, okay, and but we need something more, because then we should know how to capture the carboxyhemoglobin value, is not it. So, that is one idea, one challenge, how can we capture carboxyhemoglobin with this instrument simultaneously and correct the saturation parameter accordingly, okay, is the challenge. So, that is one aspect which is some of the researchers are also working, try to measure carboxyhemoglobin by using one more wave. See, now there are 3 components. So, hemoglobin, oxyhemoglobin, carboxyhemoglobin, etc. So, how will we capture that information? So, we may have to use 3 wavelengths, right, in order to capture this information, okay. We may think that okay, 940 nanometer where carboxyhemoglobin is very small, it will give us 2 values, but at 660 nanometer all the 3 are present, okay. So, we will have to eliminate carboxyhemoglobin component, right, somehow to estimate the other constituents and indirectly even this carboxyhemoglobin. So, we will need one more wavelength. So, based on some estimates, okay, calculations, of course, simple algebraic calculations, we found that the one more wavelength in this region between 620 to 640 nanometer, if we have one more wavelength to capture this information, then it will help us to derive all the 3 parameters, okay, from this saturation measurements, okay. So, 3 wavelengths, not 2, but 3 wavelengths, okay. So, that is one aspect, okay. Now, I will show you that there is one more application of this absorption spectroscopy in order to derive, okay, information related to some of the metabolic activities in the body, okay. So, this see generally maybe first I will show you. So, generally when we inhale the air, inhale air, ambient air, that inhaled ambient air through alveolar means through lungs, no, where alveoli will interact with the blood, right, indirectly for a gas exchange, okay, for a gas exchange. So, CO2 will be extracted from, right, blood and oxygen will be injected, right, through this. So, that activity happens in the lung. So, when we inspire air, alveolar gas exchange takes place and then the blood supply accordingly, right, is enriched with oxygen. Of course, if in the ambient air, if there are any other gas compounds such as some of the volatile organic compounds, they may also get mixed, okay, with this blood, and so some amount of blood, right, will carry such other compounds as well, other gaseous species as well, okay, other than nitrogen, oxygen, CO2, some trace amount of volatile organic compounds, water, etc., will get, right, captured in this. Now, in body, due to various metabolic activities, due to excretion activities, and due to right of digestion activities, etc., volatile organic compounds are being generated, okay, due to various activities. Very small amount of trace amount of such compounds are also generated. When I talk about volatile organic compounds, means there are some of them are mainly organic compounds, and some of them, although it is not right mentioned here, some of them need not be organic compounds, inorganic compounds such as ammonia, etc., are also present, okay, in such because see, ammonia comes into picture due to nitrogen presence and metabolic activity will generate some ammonia, okay. Now, this right ammonia is being extracted, okay, and will send through to kidney, etc., and then so if the renal activities are not performing well, or if the liver is not in position to extract that ammonia and remove it out of the, then that ammonia will remain present in the in the blood samples, okay. And so when we exhale through pulmonary artery, when the blood is coming back to lungs for air exchange, for alveolar gas exchange at that time, and then when we exhale the air, expiration process, we may see such molecules, presence of these molecules, okay, we may be able to observe, is the idea, the hypothesis, right, in our mind. So, if we observe such in the exhale some such trace gases, they may have they may indicate the anatomical physiological activities, right, in the blood, okay, they may, right, indicate that way. Indirectly, something is having some pathological conditions are there which are indirectly affecting this, right, and our human exhale breath may have the presence of such molecules will be present. Now, this presence of this molecules will be of the trace amount, okay, very few parts per million, okay. Some of those samples, there are more than 1000 maybe such biomarkers, okay, many such gaseous molecules are present other than major constituents, nitrogen, oxygen, some small amount of CO2, etc., and some other atmospheric gases. But other than that, because of the metabolic activities, because of the kidney excretion, because of the digestion activities, etc., whatever trace gases are generated, small amount, if they right in their maybe dissolved form or undissolved form, they are present in blood, they will be present in blood and maybe extracted, maybe exhaled out, right. And those such compounds are some of them, only few of them what I have put here, right, methane or pentane, acetone, ketones, basically hexane, ethane, ammonia are present. Now, they have some relationship with the metabolic activities. Basically, the presence indirectly is due to some metabolic activities or pathological conditions. So, pathological conditions, let us say if it is a healthy person, normal, of course, this is just approximate value because it depends upon various other factors also, age, conditions, demography, etc. But generally in healthy persons 3 to 8 ppm is methane, okay. But due to the pathological conditions, the concentration may change, Okay. So, if we can capture human axle and then try to derive this variation in the concentration of this species such as methane, pentane, acetone, etc., they may help us to indirectly derive pathological right conditions is the idea. Of course, they are not exactly indicate, they may be only a biomarker. Okay. Its presence in a small amount increase or decrease, you cannot simply derive that okay, the if acetone is increased, okay, the person is diabetic. Okay, it may be due to some other factors as well at that instant, but it is a one of the very important indicator biomarker. Okay. And you may need further such analysis to even extract this conditions. Okay. So, it is diabetic conditions or pathological conditions. Okay. That is one idea, one topic. However, how do we measure such trace gases, such biomarkers is the right challenge. If we can measure from human axle, then we need not worry about biopsy etc. While we remove the tissue, go for analysis, remove the blood sample, take it to the, if we can implement some idea in terms of clinical measurements of human breath, then it is a very good non-invasive approach, right, to extract the information. So, basically the focus in last maybe 15-20 years, the focus towards establishing such biomarkers, measuring such biomarkers etc., has increased. Okay. Still there are some limitations in terms of clinical applications. However, lot of interest is there in order to devise such, right, develop such devices. So, of course, I have mentioned few more as I told you, butanol or some, there are many acetaldehyde, then hexane, then nitric oxide, then even okay, it is not then hydrogen per H2O2 etc. are present. Okay. And if we can capture their information, increase in concentrations may have some relationship, okay, as a biomarker with certain diseases. So, presence of ammonia of the order of a few ppms or a few tens of ppms has a relationship with kidney or liver diseases etc. Okay. So, that can be captured. Okay. So, asthma is nitrous oxide or nitric oxide NO presence etc. But you can see that the amount of presence of this such trace cases varies from ppm, sub ppm or ppb order. Okay. Parts per billion, right, parts per million means in 10⁶ molecules, one molecule is present, correct. So, it is not very easy to capture such information, concentration of small increase in concentration, right. How to capture is the idea that for that purpose, maybe now it is maybe 1 or 2 minutes then. So, for this purpose we have various other such techniques present, okay, such as you can pick up, you can capture the human breath, take it to the spectrometer, mass spectrometer or gas chromatography analysis we can do and estimate the presence of such gases, but then it is a laboratory process, it takes few hours, okay, carrying the sample somewhere and then measurements etc. Right, etc. It takes some time, but it is possible. There are some selective semiconductor based sensor. As soon as the gas molecules are adsorbed on the surface, due to the photo redox reductions and oxidation reactions taking place between the gas molecules and the semiconductor material, the characteristic of the material changes, and that indirectly indicates the presence of this, but then the selectivity is little bit challenging, because some of the gas species may have almost similar redox reactions. I cannot distinguish what exactly I am measuring, although there will be resistance change in the semiconductor material due to some gas adsorption, but we do not know what is that gas. Sometimes selectivity is missed out sometimes. So, an ion mobility is approach is also capturing a lot of this. So, its application is increasing to capture trace gases. Okay, very small compact such sensors are also being developed. Okay. But right, in some of the defense application, they are trying to use such right, presence of ammonia in or presence of such gases, which can be an indicator of explosives as well. Okay. So, those such sensors are available, but in order to measure the very small trace gases, presence of very small gases, okay, of few tens of ppm order, etcetera, is little challenging. So, optical sensing technique is considered as one of the potential, right, you can say optical sensors candidate as a candidate for such measurements. So, tomorrow we will try to see how exactly such approach, right. It is also based on absorption spectroscopy. Okay. Right, we will extend it in order to capture this information. Okay. Tomorrow means next class, in the next class. Okay.